Hello, I am Gianmarco Contino, and it is a real pleasure to be with you. Today, we're going to explore a really fundamental question. How does a normal, healthy cell in our body become a cancer cell? But even more importantly, we're going to see how understanding the why of that process is giving us powerful new ways to create treatments. It's a story of how knowledge becomes medicine. Now, before we begin, I must make a very important point. Everything we discuss today is for your information to help you understand the science. It is not, and I must be very clear, it is not a substitute for clinical advice. For any guidance about your own health, you must always speak with your own doctor. So, this is the journey we'll take together. First, we'll look at the beautiful instruction manual our body uses, its blueprint. Then we will see what happens when that blueprint gets, corrupted with errors. We'll explore the special toolkit a cancer cell develops to survive. And then, the most hopeful part, how we can turn those very tools against it. All of this gives us, in the end, a completely new map for how to fight cancer. All right, so to really understand what goes wrong, we first have to appreciate what right looks like. And that means we must start at the very, very beginning, with the remarkable blueprint for life that is tucked away inside every single one of our cells. Our DNA.
It's almost impossible to truly grasp the scale of this information, but there is a wonderful exhibit at the Wellcome Museum in London that helps. They actually printed out the entire genetic code of a human being. It fills an entire bookshelf, book after book after book, just page after page of letters. 3 billion letters. It is just an immense amount of information.
And if that bookshelf isn't enough, consider this. It's a fact that, it astounds me every single time I say it. If you were to take the DNA from all the cells in your body and stretch it out, end to end, you would have a single thread 67 billion miles long. That is enough to go to the moon and back 150,000 times. I have to check this number every time because it seems impossible. It is by far the most efficient storage system known to man. So we have this incredible library of information. But this library isn't sitting on a shelf. It's being used constantly. Our cells are dividing, our tissues are renewing, and every time, this entire library has to be copied. And with billions of letters being copied over and over, you can imagine that sometimes a mistake can happen. And that brings us to what happens when the blueprint gets corrupted. Think of it exactly like a typo in one of those giant books. A single letter might get changed or maybe deleted. In biology, we call these typos mutations. And where do they come from? Well, they can come from the outside, things like sun exposure or smoking, but honestly, they can also just happen. It's a natural consequence of the cell machinery doing its job over a long life. It's a part of aging. Now, this might sound a bit alarming, but the wonderful news is that our body is not defenseless, not at all. In fact, it's brilliantly prepared. It has at least 3 layers of defense. First, for most genes, we have 2 copies, so there's a backup. Second, we have these amazing molecular machines that act like repair crews, constantly proofreading and fixing the vast majority of these typos. And third, if the damage is just too much to fix, the cell has a final option, a self-destruct button. And managing this final, critical defense is a key player, a protein so important that it is often called the guardian of the genome. Its name is TP53. And when this guardian detects serious damage, it makes a choice. It can call halt, stopping the cell from dividing to give the repair crews time to work. Or, if the damage is truly beyond repair, it makes the ultimate call. It pushes that self-destruct button, a process we call apoptosis, and the cell destroys itself for the good of the body. So, we have backups. We have repair crews. We have this guardian. Cancer, then, is what happens when a cell, through a series of very unfortunate events, manages to bypass all of these safeguards. It accumulates just the right kinds of mutations that allow it to break the rules. It's as if it builds its own illegal survival toolkit. So what's the first tool in this new rogue toolkit? It's the ability to simply grow and grow and grow without listening to any instructions. You see, a normal, polite cell waits for a go signal from the body. A cancer cell, it learns how to shout go at itself all the time. The accelerator pedal isn't just pushed down, it's jammed to the floor. So how does it actually jam that pedal? Well, let's look at this simple drawing. On the outside of the cell, we have these receivers, these antennas. One you may have heard of is called HER2. Normally, it waits for a signal, but a mutation can break it, leaving it permanently switched on. And it's not just the antenna. Even the wiring inside can be faulty. A protein inside the cell, like one called KRAS, can get stuck in the on position, sending a constant, frantic message to the cell's headquarters: divide, divide, divide. Now, this is where the story takes a turn. And it is, I believe, the most hopeful part of everything we do in cancer research. Because everything the cancer cell does to survive, every tool it creates for its toolkit, also becomes its weakness, its Achilles heel. Every strength is also a vulnerability that we can target. So if we know the accelerator is jammed on, what can we do? We can design a drug that specifically blocks that jammed part. For example, if we find that the HER2 antenna is the problem, we can use a drug called trastuzumab. It's designed to find that specific antenna and shut it down. If the problem is the internal wiring, like KRAS, we now have drugs that can target that too. It is truly like designing a specific key for one specific lock.
Okay, so the cancer cell is dividing and growing into a small mass, a tumor. But very quickly, it runs into a big logistical problem: starvation. The cells in the middle start to suffocate. They're too far from the body's blood vessels to get food and oxygen. So to survive, the tumor has to learn a new trick. It has to build its own supply lines.
And this is how it does it. It's really quite ingenious in a terrible way. The starving part of the tumor starts pumping out an SOS signal. It's a chemical messenger called VEGF. This signal spreads to nearby blood vessels and essentially tells them, "Help, we need supplies." And the body's vessels respond. They start to grow new branches, like little roads, right into the heart of the tumor. This process has a name: neoangiogenesis, new vessel creation. So if the tumor is sending out this SOS signal, what if we could block it? Well, that is exactly what we can do. We have developed a class of drugs called anti-angiogenics. They act like signal jammers. They intercept that VEGF message so the blood vessels never receive the order to grow. The new roads never get built. And by cutting off its supply lines, we can quite literally starve the tumor. All right, the tumor has its foot on the accelerator, and it has built its own supply lines. But there is still one huge enemy it has to deal with: our own immune system. You can think of it as the body's police force, constantly on patrol, looking for anything that shouldn't be there. For the cancer to survive, it has to learn another trick: how to hide from this police force. And one of the most remarkable ways it hides is by using a kind of secret password, a molecular handshake. The cancer cell displays a special protein on its surface called PD-L1. When an immune cell, a T cell, comes along to investigate, it has a receptor called PD-1. And when PD-1 on the T cell shakes hands with PD-L1 on the cancer cell, it delivers a clear message: "I'm one of you, stand down." It's an off switch that puts the immune cell to sleep. And this discovery has led to a complete revolution in cancer treatment, which we call immunotherapy. We have developed drugs known as checkpoint inhibitors that do something beautifully simple. They just get in the way. They physically block that handshake from happening. By preventing that stand-down signal, it's as if we are taking the brakes off the immune system. We reawaken the T cell, and suddenly it can see the cancer for what it is and do the job it was always meant to do. So you can see a pattern here: relentless growth, building blood vessels, hiding from the immune system. Over years of dedicated research, scientists have identified a whole collection of these essential tricks. We call them the hallmarks of cancer. And together, they don't just describe the problem, they give us a map to the solution. And this slide really brings it all home. On the left, you see the map of the problem, the cancer's toolkit, all the abilities it needs to survive. And on the right, you see our answers. For every single one of those hallmarks, that deep knowledge gives us a potential therapy. For angiogenesis, we have VEGF inhibitors. For avoiding that self-destruct command, we have drugs to reactivate it. There's a beautiful symmetry here. For every trick, we are learning how to design a countermove. And that really is the heart of the matter. It is the one single thing I hope you take away from our time together today. Our fundamental knowledge of what causes the cancer cell to survive has become our most direct and powerful path to treating it. The problem itself shows us the solution. And I want to end on a personal note. All of this work, all of this science, it does not happen in a vacuum. It is driven, it is inspired, and it is made possible by patients, by you. Your courage and your partnership in this research is what allows all of this progress to happen. And for that, we are all deeply, deeply grateful. Thank you.